Jnanam paramam dheyam. Knowledge is supreme.
So the next one, which is a different potential energy, is also familiar to you, it's not new to you, it's the hydrogen atom, right. So what do we assume in the hydrogen atom? We assume proton to be very heavy. Even if it is not heavy, you know what to do. What do? Introduce a reduced mass. But let's take it to be heavy in comparison to the electron, and all your chemistry way of handling is, you can call that as 1s shell, 2s shell, 2p shell, and so on, right. And you can also write, here you can put the lines with the exact degeneracy. 1s shell is principal quantum number n equal to 1, L equal to 0, but you can have the red line and this one are the two spin states possible, so it is two-fold degenerate, and so on, right. 2s shell is again going to have both n equal to 1, L equal to 0, but why have I put 4 lines? Is that allowed? No, right? Yes or no? No. So it's not right. Yeah, everything is written as 2s, so I made a mistake. Okay, so you understand what exactly you do in your chemistry course. 1s is two-fold degenerate, 2s is two-fold degenerate, 2p will be 6-fold degenerate, and so on. Okay, so you can, and the potential energy is a central potential, which is 1 over r potential. Once you see this 1 over r potential, you know what coordinate system to choose. Spherical polar coordinates, because r, then you can separate your potential energy to be only acting on the r coordinate, other potential energies are not there. So Cartesian coordinate is not a good coordinate when you want to solve hydrogen atom problem. We mechanically put in spherical polar coordinates and solve it. The reason is that the potential energy becomes dependent only on the radial coordinate. So it's better to work on the r theta phi coordinates. No point in working on xy. You can work with xy z, but then it becomes more complicated. So choice of coordinate, spherical polar coordinates is convenient, and you can choose, because u of r theta phi is actually u of r only. There is no theta phi component, and we can write the separable wave function as a product of the radial dependent, the theta dependent, and the phi dependent. So the Hamiltonian for the hydrogen atom in 3 dimension, you can write del squared and compactly. I am not writing explicitly what this Laplacian is, but you know what to do. And there is a 1 over r. So substitute r theta phi and rewrite your Laplacian in the spherical coordinates, and then what do? You try and separate out the 2 equations, right. First let's write this whole solution, and you can see from here there is an r dependence here, and theta dependent, phi dependent. So we'll try and separate it out the conventional way we did. First write psi as r of r, omega of theta phi, and then we put omega of theta phi as the theta dependent and the phi dependent. We'll do it in 2 steps to make things. Incidentally, when I am typing these equations, I might have made some mistakes. If there is any mistake, please bring it to my notice. I have to edit it. Okay. So this is the usual conventional way we try to do. Only thing is we are trying to divide by an r squared also, so that we get terms which are r of r dependent piece, omega of theta phi dependent piece. This is r dependent piece. How will you write? You will write this plus this last term to be some E1 times psi, and this plus this to be E minus E1, something like that. Okay. We can rewrite so that theta phi dependent terms are equated to r dependent terms. There is a d by dr here. Yeah. Excellent. Yeah. So there is no psi here. Okay. Yeah. Probably I have taken care of it here. This should also be d by dr. Yeah. So as he pointed it out, that psi is not there. Yes. So this is one constant which is explicitly dependent only on theta and phi. There is another equation. You split it up into two pieces. One dependent on theta phi and another dependent on small r. So the next question is further. The first top equation, we will try to rewrite it. Again breaking it up into a product of theta and phi and divide by that. So you have an equation which is, this is familiar. What is the solution here? Solution is like the same problems which you have been doing. Exponential. And this one will be, this is a non-trivial. So having got these equations, you can go back and look at special functions and see what the solutions are. So in order to make contact with the actual physics with which has this magnetic quantum number, we take alpha to be minus m squared and then we can solve this. Solution will be a e power I m phi. Equivalently, you should also know that this phi is an angular coordinate. Phi goes from 0 to 2 pi. If suppose I put phi to be 4 pi, it should be same as the 0 coordinate or 2 pi coordinate. That will kind of fix for me that this m cannot be fractions. M has to be integers. The single valuedness of the wave function in the angle coordinates, like unlike your free particle in the real line which was e to the I kx, where k can be anything, here if you put it on a circle or an angular coordinate with identification of 0 with 2m times pi, you will be forced to choose m to be only integers. That is why the magnetic quantum numbers are also integers, which is consistent. So this is what I am saying, that the single valued wave function, that the phi dependent p's have to satisfy this, which implies m is an integer, and then we get to the theta dependent equation, substituting that constant alpha which will be there, and this is the equation to solve. So you can see that the theta, the capital theta, that wave function will be dependent on the value for m also. This equation has this m. So make a change of variable just for convenience, and then the equation is nothing but our familiar Legendre, associated Legendre. So this is the differential equation for associated Legendre polynomials. So what are the solutions? You can compactly write the solution just like the way we wrote for Hermite polynomials, some kind of a compact Rodrigues formula. You can try to write it. For a specific L, L is the azimuthal quantum number, M is your magnetic quantum number. Because you know chemistry, you can try to give the meaning in the same way so that we remember them. Okay. And just play around and work out for L equal to 1, L equal to 2, just to get a feel of how these associated Legendre polynomials are. Okay, so I did not say what the C is. For this solution, the C has to be, minus C has to be L into L plus 1, and they have to be non-negative integers. That is also important. To make contact with the differential equations for special functions, you can compare the C to be this, where L is a non-negative integer. And your magnetic quantum number, which is there in your associated Legendre functions, Legendre polynomials, have to be restrictive. It cannot be arbitrary. It has to go from minus L to plus L. This is all implied by looking at this differential equation, matching it with the differential equation for special functions in the mathematics. Okay. We are not doing anything here by any other method, but we will get to it in some other fashion when we are doing it from the Dirac formats. Okay, so what is the final theta phi dependent part of the wave function? We have already seen it is e to the I m phi for the phi dependent piece. Now we have also argued that the theta phi dependent piece, which you can write the theta cos theta as x, as a Legendre, associated Legendre polynomials. This product of PLM e to the I m phi is always called in the literature as spherical harmonics, okay, and it is denoted by a capital Y Lm theta phi, okay. So we will come to these issues of playing with spherical harmonics, but this is the connection. The associated Legendre polynomial multiplied by e to the I m phi together is called as a spherical harmonics. Normalization is one thing which you should work it out, at least for a specific L and a specific M, but it can be determined for a general L and M. How do you do the normalization here? Integral of d theta alone, or you have to put d cos theta. D cos theta and d phi, you have to integrate. Cos theta, theta goes from 0 to pi and phi goes from 0 to 2 pi, and then you have to fix the normalization. Okay. What is left? The radial part. Done the angular part, we need to do the radial part. So we substitute that capital C, which relates your omega theta phi, okay, with plug it in here, and this is what you get for the radial part of the equation. I have already inserted a small n here in anticipation. What is the anticipation? This L is dependent there. This differential equation is exactly like your what special function? Associated Legendre polynomials. If you go and check special function polynomial for associated Legendre polynomials. So this is the differential equation satisfied by associated Legendre polynomials. We are not deriving them, we are just matching with what is known in the differential equation context right now. So what is the solution? Solutions are given in the literature. If you remember, I was trying to give you this Gram-Schmidt orthogonalization for function spaces, and I was trying to say that you should put a weightage factor so that it's, and this hydrogen atom, the radial coordinate goes from 0 to infinity, right? The square integrable functions. So you have an e to the power of minus half r, or a function of r, I am calling it as rho r, and the associated Legendre polynomial, and there is a condition that n and L are not arbitrary. Your L should always be less than or equal to n. Less than or equal to also? Less than n. N should be greater than n. Okay. So this rho r which I have written is just a function multiplied, it's proportional to r, but there is a Bohr radius a0 attached to it. Okay, so this is all from matching with what is there and what we know by convention, what is the Bohr radius. We can try to write this solution in a very compact fashion. This is a minor thing to do. But given some differential equation here, to find a solution, if it is familiar from the mathematics literature, we just pull out the solution and rewrite all those variables accordingly. Okay. There E may not be energy, maybe some constant, but now we can try to write that energy is in terms of those. So En is proportional to 1 over n squared with a negative sign. So why a negative sign? Bound state. Positive solutions are allowed or no? Positive energy? Not for the bound state, but you can have scattering states. You can sit and play around for a specific n and a specific L and see whether you get the normalization. Here the normalization will be integral over dr r squared should also be there. Explicitly the normalization in 3 dimension, it's integral dv psi star xyz psi xyz. This should be 1. dv in Cartesian is dx dy dz in Cartesian. In spherical polar it is dr r squared sin theta d theta d phi, right? So now I am trying to say that if you write your psi as a function of r theta phi as omega theta phi times r of r, then integral sin theta d phi omega of theta phi mod squared should be 1. What about r squared? Mod r squared will be multiplied by this piece. Okay, so you will have mod r of r whole squared dr r squared. This is purely coming from the Jacobian. When you take x, y, z to r theta phi, these factors are coming out of the column. Many of the students, my last so many years, is that they forget about these r squared when you do the normalization. But when you go to spherical coordinates, there is a non-trivial Jacobian, you have to remember that. So it is r squared dr sin theta d phi mod omega theta phi whole squared mod r of r whole squared. This has to be 1. That is the normalization. You can split it up into r piece and theta phi piece, but the normalization has to be with the volume factor in that appropriate coordinate. What happens in cylindrical coordinates? So suppose I write psi rho phi z, there will be a dz rho d rho d phi. Okay, you understand? You have to remember this. Many of them forget these things and then it leads to completely wrong physics. Okay, so let me stop here, that it is an associated Legendre function, and I will put this up for you and you can verify a couple of things. So the next lecture I will continue a little bit on how to get into the Stern-Gerlach experiment, and then we will see what I should do the following Friday.